Hello, it's James from XRobots.co.uk. This is part 24 of Ultron, the Real Robot. This episode is mainly finishing off bits and pieces of the mechanical design so that we can move on and do sensing and AI. So there's still some cosmetics to do. I've also got hands that I need to do at some point, but we'll come back to those. But in this episode, I'm going to sort out the rest of the head animatronics. At the moment, the jaw is a bit slack. We're going to put some lighting in, and I also need to install the series elastic actuator so we can read force feedback. But before I get onto that, I'd like to tell you about a website called Alltimelines.com. Alltimelines.com belongs to a patron of mine who supports me on patreon.com called Jason Hamilton, and Alltimelines.com provides chronological timelines of popular fandoms, basically including Star Wars, Marvel Cinematic Universe, DC and various others. So there's an interactive element to this. If we go to Star Wars, for instance, we go to Star Wars Canon. We've got the choice there of Legends or Canon, and we can see the timeline here. So these are basically films, books, TV, games, that sort of thing. So if I don't want to look at television series, I can click on Hide Television, and all we get is the rest. I can hide films as well if I want. There are many other franchises included in this, so let's have a look at Doctor Who, which is one of my personal favourites. So obviously we can see here there's various things in the timeline. We can also sort by author as well, or by type, or whatever we want with these columns. So we can just sort that the other way. So you can pretty much sort through anything you want to sort through. So Jason actually started doing this website in March 2016, so March this year, but he's added a lot of content recently for the main launch. There's also a blog which is going to be updated regularly on the blog link here, which has already got quite a lot of posts on, and new content is going to be added weekly. Jason has created Alltimelines.com because ever since he was young, he basically wrote down these timelines to get his head round some of the more complicated ones. He found his friends really enjoyed it, so he decided to turn it into a full-blown website. As I say, Jason supports me on patreon.com, so you can have a look at patreon.com/xrobots if you'd like to support my channel. Alright, let's get on with Ultron's jaw. We need to animate Ultron's jaw, which I'm going to do with a normal servo, but it needs to go right in at the back there to pull it up and down. But fortunately I left this so I can remove the top of the head, so I can make a bracket to stick my servo on that mounts on the stick that's left behind. We can then have a connector to remove the top of the head with any associated wiring. That's going to include some lighting and also potentially sensors in the eyes in the future. I made this 3D printed servo bracket in ABS so I can solvent weld it onto the existing part. Then we can select a servo horn and a lever to go and activate the jaw. Just going to use a little bit of acetone in a pot here with a brush, and we're just going to make a solvent weld, which is how most of the other bigger parts are stuck together. And then we can stick those together and make a nice solvent weld. I've installed a little lever here with the bottom pieces solvent welded on, so there's a hinge top and bottom. And of course this will move the jaw up and down now, so if we just pop the head back on, you should find that looks okay. And obviously when it's at the top, the jaw is closed. And at the bottom it's down. There really isn't that much motion, as there isn't when you talk anyway. The next plan was going to be reinstalling all these bits of cosmetics and putting in lighting throughout the head and torso. Before I do that, I need to take apart all the joints and install some force sensitive resistors. All these hubs have pairs of force sensitive resistors that will sense motion in either direction, and that makes up my series elastic actuators, and I did some research early on in the early episodes of this project. So basically if someone grabs one of the joints and pushes it around, it can sense the force, and that's going to make up part of my sensing. Here's a force sensitive resistor. Basically you squash it, and as the name would suggest, its resistance changes. So I've got one of them attached to a breadboard here and attached to my meter. It's on currently the 2000 ohm range, so the 2K range. As I squash that, we should be able to see this coming down. I think the lowest I can get out of it is about just over 200 ohms, and it goes all the way back up to infinity. So put that on the 20K range now. Should be able to see I can touch it a lot lighter, so that's 1.2K. all the way down, pretty much to the same rating. So I've got packing in my joints, and I need to fit these with something squashy either side so I get a full range of resistance when the joint moves. Each of my three main shoulder joints has provision for two force sensitive resistors to be fitted to make the series elastic actuator for that joint. So I've got 12 force sensitive resistors altogether to fit. There are slots in the top here, but I do need to take these to bits to put them in, and then I need to put packing in, which is basically where the force sensitive resistor fits, and also on the opposite side to the joint to help pack it out so I can get the right sensitivity. I installed a connector here so I can easily take the arm off, and then it's just 4 screws to remove it all together. So I should have left the ability to take this to pieces, so I should be able to take off this bracket here with 2 screws, and then hopefully I can undo these nuts and we should find that the arm drops to pieces there and I can get the full sensitive resistors in. So now what we should find is we've got these slots to let the wires out from the full sensitive resistors. I put some packing in this one, so we need to take that out. And then obviously when this is together, they push against these things here. So that means we can measure force in each direction. We've got 2 sides to this, one for packing for resistance and one to put the actual resistor so that it gets squashed, which means we can limit the amount it gets squashed as well. Here's the Adafruit tutorial for wiring these, and obviously unlike a normal potentiometer there's no wiper and a track. It's only one piece of resistance that changes. So essentially you need to wire this like a potential divider with a 10k resistor on the bottom, and the analog voltage comes out the middle, and the full sensitive resistor in there is between that analog voltage and 5 volts. So essentially I guess anything that gives me a resistance down to about 1k when I press it is going to be an okay range to give me an analog voltage I can work with coming out of there, which is going to be 10-bit anyway. So I've just fitted in there some foam PVC board, you can just about see, with some bits of styrene stuck either side just to make it a bit bulkier, and my full sensitive resistors stick out the back there. So that fits pretty well. I was going to 3D print something, maybe a hybrid print of ABS and maybe NinjaFlex or something else flexible. But if this works well, we might leave it at that, or I might make some ABS parts. Obviously there's no packing in the back here. For some joints that's going to need to be there, and for some it maybe doesn't need to be there. I've just reinstalled my joint here on a piece of temporary studding, and I've just connected the meter to that full sensitive resistor, so you can see the reading here. I've put it on the 200k range because it's not quite sensitive enough. But if I do this, we can see I can get down to about 2k. Really need to go a bit lower than that, and that's pushing quite hard. So I probably need to put in some more packing there to push the full sensitive resistor more. Just doing a little experiment on the edge of the table here. I've got some of this sort of double-sided foam tape, and I've just put a piece on there stuck to the table, and I'm just trying pressing the full sensitive resistor, which is working pretty well. I can easily get down to less than 1k there. And also if I press through another piece of tape, so if I do this and push through it, that's also quite easy. I'm not applying very much pressure there, which means it's working quite well. Now with these bits of tabs, obviously the load was spread between the tabs as well, instead of pushing down directly on the actual full sensitive part. So I think what I'm going to do in fact is stick the resistor inside that joint with some of this red tape, then 3D print varying thicknesses of round discs to stick on the other side with some tape that actually do the pressing. And we'll see how that goes. Just experimenting with some different size parts. Don't know if you can see they're slightly different heights between 3.5mm, basically the middle one's 4mm and 4.5mm. And I'm printing those on the TAS in a 0.2mm layer height. So hopefully we get a varying degree of accuracy there, and we may need to tweak it and maybe lower the layer height to make it even more accurate, but I'm hoping one of those will do at least for testing. I've used the shortest ones for now, so hopefully you can just see them in there, with the full sensitive resistor stuck on either side and the little lump stuck on the top of it. So we can see in fact that just with this inserted in here, we can see it's already measuring something, and that's on the 2k range, so just under 2k. If I turn away from it, then it will go open, and if I turn towards it, I can get all the way down to sort of, well under 1k, about 400 ohms. So that seems to work pretty well, and the opposing one, which is in the other side, does pretty well as well. So whether I need to pack out this side, I'm not really sure. I don't think I do for this joint, because I can always put a threshold in, at which point it's actually measuring force rather than just measuring the joint moving and the resistance in inertia from the piece that's still. But I can still put packing in here so that there's less force applied to these, which is a bit like a cushion if I want to. I've installed the full sensitive resistors in both arms, but I'm leaving those off for now to help me do the hubs here and mainly the big shoulder hubs. So with these, sensibly I left the ability to take these screws out so I can take the pot off the bottom. Then it's just a case of unscrewing the bit of studding. You can see the top there and the washers it goes to in at the bottom. So that should slot out and I could take this whole thing out then. Had to take the motor out to get the piece of studding out, but basically this has come free now, and this is an identical part. It's actually identical CAD, so I can use exactly the same tabs and all the printed parts and stick those FSRs in with tape. So those are installed in these hubs. You can see the terminals just sticking out there. Of course, this thing doesn't have a massive range of motion, so the wires don't get twisted up. I'll wire them in and strain relieve them, but this doesn't go round and round and round, so that should be fine. The next ones I have to do are the force-sensitive resistors in these big shoulder hubs, which of course carry the whole weight of the arm, and the outside rotates independently from the inside. So even though the actuator is this linear actuator down here, of course the load of the arm is on the hub, so that's going to work just as well for the series elastic actuator. And I cleverly left some screws here which I can take out. I can take away one of these, the back or the front, so that should make it much easier to disassemble to put the force sensitive resistors in. So I've unscrewed those screws and that just comes off and everything's great. So I've already put some blocks of Ninja Flex in here at some point and we can see the inside moving now, but obviously the series elastic actuators go in those two slots and the wires come out through these two holes, so that's going to be pretty good. And the one thing we have to consider, of course, is that this one needs to be buffered more than this one, because that's the weight of the arm. So this one basically probably needs to have a thinner thing on it, so more load is taken by this opposing piece of Ninja Flex. Right, I've installed the force sensitive resistors on some little styrene tabs there, so they go in and they don't go any further. And you can see there that I've put the force sensitive resistor on the thing there with the sticky tape, and I've stuck a 3D printed thing on, so with a bit of trial and error I think I've got it just about right. So I've just put the meter, you can see the reading there, that's onto the bottom FSR at the moment, and we don't get much out of it because obviously there's not much load on it till I lift it, and then we get some stuff and I get approximately between 20k and just under 2k, which is okay, I guess. And obviously I need to combine both of these to give me a value that swings around 0, so I can do some of that in code. So now I'm going to change that over to the top one that actually always has some force on it because the arm is pushing down. That one's already reading 1.47k, and if I lift the arm we should see in fact that value goes up, and if I push it down it goes all the way down, yeah, well less, about 500 ohms, so I get quite a good range of motion there even out of one of them. So I can of course just combine these, even though I haven't managed to tune them up mechanically to be of similar ranges. I can combine those either electronically or in code so that I can actually get quite a good range of motion when someone pushes or pulls that arm. I've installed 12 force sensitive resistors, so where am I going to read all those analog ins, you might ask? Each Arduino Mega has 15 analog ins. There's almost enough on the Arduinos that I've installed, but I actually have other sensors to read, so I may well install another Arduino Mega to read all that sensor data, and it may also be the Turnpike Arduino Mega that reads the serial data being sent to the robot and sends it out to the 3 Arduinos for each side of the body and the head that are already there through its extra 3 serial interfaces. Haven't quite decided if that's what I'm going to do, but hopefully I'll need to decide in the next episode or two so I can actually get this working and we can read some sensor data and make the robot react. But for now I need to install some lighting. The lighting is going to be made from NeoPixels, or WS2812s as they're known, and they come in various configurations. This is in fact a sheet of individual ones which you break apart and solder to individually. All of these can be daisy chained, so typically you have an in and out and a power. And also I've got some rings here, and I've also got a long strip here which comes in a silicon casing, but I've also obviously cut that out at some point and used it in some project. So we're going to have some of these in the head, some in the torso, and later on we'll have some down in the arms. I want the lighting to look quite diffused, so I'm going to take one of these and put it inside facing backwards behind these cosmetics, probably so it illuminates the stuff inside that you see through the cosmetics. Probably going to do the same in the torso here with another one, but put it right back inside, maybe pointing down if I can do it. I'm probably going to cut some NeoPixels off the strip and stick those in the back of the head above where the servo mounts so that they shine forwards. The eyes will eventually have diffusers in any case, and the eyebrows, if you remember, were going to be filled in with animatronic parts, but the light should shine out nicely for whatever sensors I have in the eyes if I have some, and also out through the slots in the top of the head. If you remember, the top of the head is removable for easy access. So that's my NeoPixel strip taped in there. And we need to put a connector in for that servo as well. And then we need to have a removable connector. And I'm going to use these 25-way D-range connectors so that I can unplug the head. Just soldering up this connector so I can wire in my NeoPixels to the head. Here we go, we're getting there. So that goes to the servo that's in there and the NeoPixel strip, and that's my nice connector so I can take the head off. I've installed a little bit of strip board here to act as a power sort of strip for all of those NeoPixels. Eventually I'm going to cut into the 5 volts from the big power supply that powers the servos, and also the grey wire here is the NeoPixels into the head, so I need to cut some tracks and go in out for the other NeoPixels. Here are my other NeoPixels ready to be installed, so I've got the in and out wires both wired up as well as power, and those will come back to the same board. I've just chucked an Arduino Mega in the back there for now, which is the one that's now controlling the NeoPixels, and it will probably read all the sensor stuff as well, but we'll have to see how that goes. I've just turned the lights on to full brightness red, which looks pretty good, and obviously they'd go full brightness white, which would be 3 times brighter using all of the RG and B LEDs in there. But for now I think that'll do. It looks pretty good. Obviously the LEDs are RGB addressable as well and individually addressable, so I could do all sorts of fancy mood or lighting patterns or anything I wanted really. But for now I'm pretty happy with the way that looks and the way that it moves. Yeah, the head's a bit wobbly, but that's something we can sort out. Last thing I'm going to do this time is wire in all of those force sensitive resistors I installed into the Arduino Mega, and we'll try and make some sense of the data. So I've made up a rather nasty board with a lot of 10k resistors on as per the Adafruit diagram I showed you earlier. So that's linked to all of the 12 analog ins and ground and 5 volts. And they go out to another one of these great D-range connectors. The other half, of course, will get wired to all the force-sensitive resistors in the robot. So this is an Arduino Mega, and that's going to deal with all the sensing for the robot. So eventually this will be mounted in a nice box somewhere with other sensors connected to it, and then that will send data back over Bluetooth to the AI. So now on the back of Ultron, I've wired in all of those force-sensitive resistors into this nasty board here, which plugs into the first board. And that goes in there just like that. And that, of course, is connected to the Arduino Mega, which is then plugged in with USB to my computer so we can read all the data. Right, I've written some pretty simple code here, which takes the force-sensitive resistors and does analog reads on them all and then just prints them out to the terminal. So if I now open a serial terminal, we should be able to see those pairs of numbers, and you'll notice there's a 0 accompanied by a number in each case. And these are the 6 pairs of effectively force-sensitive resistors that make this series elastic actuators. The first column is its left arm on this axis, so if I get that and grab it, we should see those first columns switch over as I push it in different directions, and if I'm very gentle, we can get some granularity there where it switches over and the results vary from 0 up to about 900. The next joint is moving the arm here, so we should see the next 2 columns switching over and then lifting the arm, and that's the next one, all the way over to this side where we have the same thing on the far right column. So that seems to be working pretty well. All I need to do now is combine those numbers in code, and then we can get results for each pair. So I've done something very simple here, which is just to get these variables called pair. And all I've done is basically multiply one of those values by -1 and added it to the other one. And that now gives me a plus-minus swing. So if I go and grab I've now got, of course, 6 numbers here for the pairs. So the left-hand column here is this one. So that gives me a swing somewhere between minus and plus 900 with a lot of values in between. There we go. Obviously the column on the other side is the other arm there. If I twist that one, I probably do need some more packing in there because there's not too much in the middle and there's still a bit of a dead spot. Particularly it's noticeable if I lift the arm, which is this column here. We get quite a big dead spot actually where it's sort of floating in the middle, but as I push it up that number gets higher, and as I let it go down it gets higher in the opposite direction. Of course, one is swinging negative and one is swinging positive. That's the same for the other numbers as well, if I move this whole thing around. So yeah, I probably could do with some packing, and I'm not sure if these numbers are going to be super useful as they are, but obviously now I've got the numbers, I can work out where I need to put something spongy, perhaps particularly in these joints, in those opposing places opposite the force sensitive resistors, where I had space for some NinjaFlex or a low density printed NinjaFlex, which of course gets softer, or I could put foam in. So that's really the basis for the series elastic actuator feedback. Next time I'm actually going to be taking that sensor data, now that I've got data I can read from the robot, and then making the robot react to it. So it's a bit like it's sort of instinctive reactions, if you like. So if I shove Ultron, what does it do? Does it look at me? Does it move with me? If I grab its arm, will it then move its arm up with me and look at me and say, hey, what are you doing? Based on its AI in the future, it may push you back if it's annoyed, for instance. And those are things that I'm going to come on to, so it's quite exciting now we've done the core mechanical build. We can actually work on some more interesting features and have Ultron moving around, of course, by sending data to it in reaction to its sensing. So for now we've just got those series elastic actuators. There will be other sensors in the robot, including vision and sound and various other things that I'm going to install. So don't forget to subscribe to my channel for more updates on this project and various other robotics projects. And also you can check out my Patreon campaign at patreon.com/XRobots, where you can get access to some exclusive rewards, including a live broadcast with me and all my videos early. Once again, don't forget to check out Alltimelines.com, and thanks to Jason for supporting me on Patreon. Alright, that's all for now.